The root knot nematode Meloidogyne incognita is one of the most important plant parasitic nematodes, as it is able to infest almost all kinds of crops. The video demonstrates the infection process in Arabidopsis thaliana. Because of certain unique properties, this plant has become a model for classical and molecular genetics and therefore offers an extraordinary potential to study the interactions between host and parasite. The transparency of its roots allows the observation of infection processes within root tissue under in vivo conditions. The infective juveniles are attracted by root diffusates of the host plant. The elongation zone behind the root tip shows the highest attractivity to the juveniles. To find proper penetration sites, the juveniles explore the rhizodermis with their lips and the thrusting stylet. Quite often, several juveniles try to penetrate the root at the same site and at the same time. In most cases, the juveniles invade the root by intracellular penetration. However, sometimes juveniles also invade the intercellular space between two adjacent cells. In cases of intracellular penetration, the thin cell walls in the elongation zone seem to be weakened by enzymes. The juveniles invade and cause immediate cell death. Afterwards, they proceed to the next cell. Intercellular penetration is performed in a completely different way. The juvenile concentrates its attack on the matrix between two rhizodermal cells. It assumes a posture which is typical for penetration. The intercellular matrix is prepared for penetration by a definite sequence of behavioral patterns. After probing, the stylet is inserted into the matrix. As long as it remains protruded, salivary secretions may be released in order to weaken the middle lamella. In contrast to cyst nematodes, the stylet of root knot nematodes is not used as a mechanical penetration tool. Towards the end of stylet protrusion, the medium bulb is activated. Primarily, the medium bulb is used for food withdrawal. However, it still remains to be clarified whether it has additional, yet unknown functions during this phase. The stylet is drawn back again and the pattern is repeated. The intercellular space is now widened and the nematode has already pushed its head into it. It now enters the intercellular space and starts to migrate towards the root tip. Intercellular penetration obviously did not cause any damage to the rhizodermal cells. Juveniles which penetrated the root intracellularly leave the cells which they have entered and also proceed migration within the intercellular space. During migration, the nematode permanently repeats the pattern of behavior described before: stylet thrusting, protrusion of the stylet, followed by activity of the medium bulb, and stylet withdrawal. Successful penetration and migration is essentially dependent on the site of root invasion. The nematodes must invade the elongation zone, and afterwards they must orient themselves towards the root tip. The following two examples of unsuccessful penetration and migration will demonstrate this fact. This juvenile tries to invade the root directly via the root tip. As a response to the nematode's attack, the tissue of the root tip disintegrates and fails to provide enough mechanical support for root invasion. The second example shows a juvenile which has not oriented itself towards the root tip, but in the opposite direction towards the root's base. In this direction, the nematode becomes trapped by the thick cell walls, which impose an unsurmountable obstacle. Hours later, this juvenile is still trying to perforate this cell wall, however, without success. The following scene now shows successful migration. Here are two juveniles migrating intercellularly towards the root tip. During migration, the plant cells are almost not affected by the nematode. Only the intercellular space is widened to provide enough space for forward movement. This time-lapse sequence shows that the speed of root elongation exceeds that of the forward migrating juvenile. At higher magnification, some more details become visible. The intercellular space is widened by the juvenile, and the cytoplasmic links between the cells, the plasmodesmata, are first stretched and later interrupted. The widening of the intercellular space is achieved by subtle movements of the head end. The arrow points to fluids pushed forward toward the intercellular space in front of the nematode. During root penetration and migration, the three gland cells of the nematode are very active. Secretory granules of the two subventral gland cells gather in the two ampullae within the median bulb. Before the bulb starts pulsating, the movement of the secretory granules is interrupted by the contraction of special muscles. Granules of the dorsal gland cell are transported within its extension towards an ampulla just behind the stylet. During migration through the meristem, a considerable number of the delicate cells is damaged. Afterwards, the path of the nematode is visible by a trace of necrotic cells. The growth of the root tip is usually retarded for some time. The meristematic cells are not damaged by stylet thrustings. The nematode obviously weakens the walls and then crushes them. When the juveniles have entered the meristem, they turn round and orient themselves towards the root base in the center of the root. At the root tip, the vascular cylinder is not yet differentiated, but it gradually approaches the backward migrating nematode so that it is finally entered by the juvenile. With this strategy, the nematodes are able to avoid the obstacle imposed by the endodermis. For technical reasons, this and all following scenes are turned round at 180 degrees so that the root tip is at the right-hand side. The juvenile has now reached the region of the vascular cylinder, where it gradually slows down its forward migration and starts to induce the first giant cells. After about 17 hours, distinct changes within the cells surrounding the nematode's head are clearly recognizable. The cells have become multinucleate. Some of the nuclei are indicated by arrows. The behavior of the juvenile still follows strictly the same pattern, which has already been described for the process of root penetration and migration. About 40 hours after the induction, the central cylinder is clearly widened. The head end of the nematode is surrounded by several giant cells. These cells are pierced with a stylet, and after a certain time of stylet protrusion, the medium bulb starts to pulsate for food withdrawal. The system of giant cells is here shown about 47 hours after the induction. The multinucleate cells surrounding the nematode are extensively hypertrophied. Their development has suppressed the differentiation of xylem elements. Already differentiated elements project into the giant cell system without being connected to others. This disconnection will obviously greatly reduce water transport. About 70 hours after the induction, the swelling of the root tissue, forming a gall, prevents further detailed microscopic observations. The pumping median bulb is here the only nematode structure which can be recognized clearly. The juvenile proceeds, feeding in gradually prolonging pumping phases until it will finally molt. Within 3 days, the juvenile has induced this gall. It contains the giant cells and the developing juvenile. The extent to which the gall will grow is dependent on the host plant. In Arabidopsis, the galls remain small, often so small that the young adult females protrude from the gall.